Now, on the first page of this module, we said, okay, we're assuming right now that we know the standard deviation, but now we'll look at what if we do not know the standard deviation? What if it's a topic in which we don't know a whole lot, there hasn't been a lot of research, so we can't look at previous studies to see what the standard deviation was? Can we still estimate the population mean? In this case, the answer is yes, but we have to make some adjustments to our confidence interval formula. So on the previous page, we used confidence intervals to estimate the population mean mu. For this confidence interval, we had to use the population standard deviation sigma based on previous studies. It may have occurred to you that if we do not know mu, it is unlikely that we know sigma. So we now take a different approach. We estimate sigma using the sample standard deviation S. Notice that this is the same type of adjustment we used previously when working with proportions. The standard error of the sampling distribution for proportions involves P, the population proportion. If we know P, then we wouldn't need to build a confidence interval. We approximate P by the sample proportion P hat. So the standard error, it was equal to, in the beginning when we talked about population proportions, the square root of P, which is the population proportion, times 1 minus P over N. But if we don't know the population proportion, we estimate it with the sample proportion P hat, just replacing that in the formula for P. Our process for adjusting the confidence interval for estimating mu is similar. We use the sample standard deviation S to estimate sigma. The standard error for the sampling distribution, sigma over the square root of n, becomes now S over the square root of n, where S is just the standard deviation of our one sample as opposed to the whole population standard deviation. This adjustment affects the margin of error in the confidence interval formula, but this adjustment is not as straightforward as our work with proportions. This sample estimate for sigma introduces more uncertainty in the process. The problem is worse with smaller samples because the sample standard deviations vary more. For small samples, S is a worse approximation for sigma. Unfortunately, this approximation makes the normal model a bad fit for the sampling distribution and inappropriate for determining the margin of error. For this reason, we use what is called a T model, also known as the T distribution, for this purpose. So now we'll look at what the T model is and when to use it and what it's all about. Introduction to the T model. Okay. Here is the formula for the confidence interval based on the T model. Notice that the formula has the same structure as our previous confidence interval. Sample statistic plus or minus the margin of error, where the margin of error is the number of standard errors associated with the confidence interval. So we have X bar, as they show here, which is the sample mean in the center of the interval, plus or minus T with a little subscript of C. That represents the critical T value, which depends on the confidence interval. We'll see what that is all about soon. Multiplied by S over the square root of n, which as we've seen before, that's the margin of error. This T subscript C, the typical T value, times S over square root of n, that's the margin of error, but just S over the square root of n is called the standard error. As before, we can only use this formula with certain conditions are met for use of the T model. So when is a T model a good fit for the sampling distribution of sample means? We'll check these two conditions below before we use the T model. First, we can use the T model if sigma, the population standard deviation, is unknown. If sigma is known, then use the normal model instead of the T model, if the conditions of the use of the normal model are met, of course. On the other hand, we use the T model if variable values are normally distributed in the population. If this is not true, then make sure that the sample size is large or more than 30. Now we'll look at how does the T model compare to the standard normal curve. Okay, up to this point, we have been using a normal curve to model probability distributions, specifically the standard normal curve of z-scores, which has a mean of 0, because 0 is right in the middle of that, and a standard deviation of 1. Unlike the standard normal curve, the distribution of t-scores depends on the sample size n. Z-scores didn't matter, the n value didn't matter. There is a different T model for every n, so the T model is a family of curves. Instead of referring to n to specify which T model to use, statisticians refer to the degree of freedom, or df for short. Degree of freedom, or df. The number of degrees of freedom is one less than the sample size. That is, degrees of freedom, df, is the sample size minus one less than the sample size here. Now let's take a look at a few T model curves for various values of df, the degrees of freedom, to see how they compare to the standard normal curve for z-scores. So you can see there are a few different curves below in this model, and the peaks are higher the larger DF goes. So notice for DF equal 2, it's the blue curve, which is the shortest one, at least the peak. So notice the peak is tall, but on the sides, the blue curve is actually the tallest. The larger DF is, the higher up the peak is, but also the lower these portions of the curve are. They kind of glide down to the x-axis faster or more quickly than the blue curve. So larger degrees of freedom allow you to have a higher peak, and it gets closer to the x-axis faster as you go left or right. We can see from this picture that as the sample size increases, the t curve gets closer to the standard normal curve. And so see the black dotted curve is the normal curve. And the red curve, which has degrees of freedom 15, is almost the exact same thing as the normal curve. The larger the degrees of freedom, the more it can be close to the normal curve. And at a certain point, you probably can't even tell the difference between them. The differences are so minute as DF gets to a certain size that it won't even matter. When degrees of freedom are large, the t curve is in essence the standard normal curve. This makes sense because when samples are large, we expect the sample standard deviation to closely approximate the population standard deviation, so the t-scores will be very close to the z-scores. Okay. Similarities between the t-model and the standard normal model. What they have in common is that they're symmetric with the central peak, they're bell-shaped, they're centered at 0. The larger the degrees of freedom, the closer the t-model is to the standard normal curve, and the area under the curve represents probability. But there are differences between the t-model and the standard normal model. First being, for smaller samples, the t-model has more spread about the standard normal model. Also, the t-model has more probability in the tails, like we kind of noticed, as DF is kind of small, it's higher up at these tails on the left and the right than the standard normal curve, as you can see. We can see that this is in the fatter tails and lower central peak of the t-model, as we kind of pointed out. Now we'll talk about how do we find the t-scores associated with a certain confidence interval. So we know how to calculate z-scores from before. That was a certain, we had a certain formula for that. But now how about t-scores? As noted above, the t-model depends on the sample size. Therefore, we need to first use the degrees of freedom to identify the correct t-curve. Then we need to determine the middle area based on the confidence level. We will use an applet to find t sub c based on the confidence level and degrees of freedom. Eventually, we will just use StatCrunch or a similar statistical package that does all the calculations for us and outputs the lower limit and upper limit of the confidence level. If you end up having to take more statistics classes or more classes related to your major that use a lot of statistics, you might see that also. But let's look at this example. We use the t-distribution inverse calculator to find the t-score. So another applet that's kind of like using the z-score to calculate the probability type of thing. It's very similar to that. So, okay, in this particular example, let's suppose that we want to estimate a population mean with a 95% confidence interval. We estimate the standard error using the standard deviation from a random sample of 40 individuals. What is the value of t sub c? This is a large enough sample for us, this should be us, for us to use the t-model using the t-distribution inverse calculator to find the critical t-score, aka t sub c. That's the critical, the little c means critical t-score. Okay, so let's see what we have here. If we do that, we get these values here. So in this example, they used a 95% confidence. So that would be my central probability. I want 95% of the area to be in the middle. And the number of degrees of freedom, remember we said degrees of freedom is 1 less than n. And they had mentioned in this one here that the sample size is 40. So I want 40 minus 1. 1 less than 40 is 39. So I'd like my number of degrees of freedom to be 39. I'm going to type that in, or I can just use the little clicker to make it go smaller and smaller until I get to 39. Oh, too small. There we go. So it looks like the t-score here, the applet told me, was 2.0227. Okay. We'll keep that in mind as we go through the rest of the problem. Okay. As it says here, okay, our answer is t equals 2.0227. We set the confidence level, which is the central probability, to 0.95. That's another way of writing 95%. And the degree of freedom to 39, which is 1 less than n, 40. Note that for 95% confidence, the empirical rule approximates the critical z-score as 2. The empirical rule is based on the normal model. Using the t-model for degrees of freedom equals 39, the critical t-score is 2.0227, which is very close to 2. This makes sense because for larger degrees of freedom, ours is 39, which is fairly large. The closer the t-model is to the standard normal model, we will see that the critical t-scores differs more from the critical z-scores when the sample sizes are small, as you can kind of tell from those graphs that we saw above. Now look at an example where we estimate birth weights. Okay, so suppose that we want to estimate the mean birth weight of babies born in a town with a 90% confidence. So right away, I can just change this to a 90% confidence. It already is there, but if it wasn't, I'd put the central probability as 0.9, 90% in decimal form. Based on past studies, we assume that birth weight is normally distributed in the population. We estimate the standard error using the standard deviation of a random sample of 15 babies. So n is 15. What is the value of t sub c? So I said that we want a 90% confidence level. Confidence level is 90%. But another way to say that is that we want our central probability to be 90% in decimal form from 0.9 or 0.90, whatever. If it wasn't already at that level, I would change it to that. And our degrees of freedom is n minus 1. And they said this sample size is 15. So 15 minus 1 or 14. That's what we would set our degrees of freedom to. It's already there, but if I want to use the applet above, I would do that. And then it should calculate our t-score for us. So you could go ahead if you want to and use the applet above on this page to make sure that you actually get that t value, to make sure you're doing things right with the applet. Note, you may recall that z sub c, the z-score, for 90% confidence is 1.645. We see a bigger difference between TC and ZC because the sample size is small. The t-scores aren't doing a great job of estimating normal curve values because n is so small that it's not, the curve of the t-scores for degrees of freedom equals 14 is far away from the normal curve. But if the degrees of freedom n minus 1 was larger because the sample size is larger, then it would be a lot better.